Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system. Hi, welcome back to the show. Hi, Yannick.
Hello, David.
So last time we talked about the results of the model that I trained, and I trained using supervised learning. This week we're going to talk about what you've been doing, the way you've been training a model, which is different. So just as a quick reminder, supervised learning, that's when you give the system data, and the data has been labeled, usually by a human, a reliable human, and so it knows, the machine knows what to look for in any of the particular labeled clusters, and it learns from that, tries to find patterns, it generalizes, it trains itself better and better, we hope, and then it ends up doing pretty well in playing tic-tac-toe against a random agent.
Yes, it does. As we saw last time, your agent did pretty well. I think it was in the 80% plus win rate, so that was good. But yeah, that was a good summary of supervised learning. You basically know what the correct answer should be, and you're trying to get the model to learn that and then hopefully generalize to other things it hasn't seen.
But that's not what you chose to do.
That is not what I chose to do. So I think I've alluded in past episodes to saying, I'm digging into something and researching something. And the approach I wanted to look at was reinforcement learning, partly because it wasn't something I had much experience with. So I first wanted to start there, which is how did I come to the point where I am now in having trained an agent, given that I wasn't familiar with it before. And I wanted to talk about this because this is a question I get a lot in my day-to-day work. Somebody maybe has an idea for something, or they've seen a cool demo of some AI application, and they want to figure out how can they sort of make something like that, but for their problem. And they'll ask, how do I make this AI? So I sort of wanted to go a bit through the process of what are the steps involved from going from this idea, I want to play tic-tac-toe, and I heard reinforcement learning is good for games, to how to actually make something concrete. And the first step for me was learning about reinforcement learning, for which I used books.
Wait, books?
Books, book chapters.
Online?
Online and on paper.
What?
Yeah.
Okay, it's a little embarrassing, but go ahead.
And I have one to recommend. In this example, the sort of main reference I used was this book called Deep Learning with JavaScript. Convenient, because we're using JavaScript.
May I interrupt for 1 second? Yeah. I want to be clear. I write paper books, so that was... Okay, go ahead.
David's pro books, as am I. But also, I was able to look at an academic paper, and the one I read was about this deep learning system that had been trained to play Atari games, because that was a result that had just really inspired me when it came out. And I was like, I can finally get to read that paper with a purpose and sort of see what's in it.
It will be linked in the show notes.
Yes. These and other resources will be linked in the show notes. But my main point here is between that and just sort of blog posts online, and there's a bunch of video courses, it does take some time to learn a new algorithm. But my style of learning needs different resources pulled together. So it wasn't just one thing. I read a number of different things and then synthesized that.
You do come to this with some serious expertise in machine learning development.
Yeah, I'm already comfortable with the mechanics of the machine learning system or the thing that underlies it, and with other forms of machine learning and with programming in general. So yeah, I do come with experience and comfort there.
You're at least pretty good at it.
There's always opportunity to learn something new. So what is reinforcement learning? That was sort of the journey I was on. And I'm going to describe it as, rather than learning by example, which is what I'd sort of consider supervised learning, it's more about learning from experience or learning by trial and error.
Oh, that's good. Go ahead.
And I'll describe it sort of with this notion of there a number of ingredients to the reinforcement learning problem, and then sort of a recipe metaphor. So what are the ingredients of reinforcement learning? First is the agent, and we've already talked about agents. That's just the AI thing that's going to be playing this game. Second is the environment. And the environment is the world.
I'm sorry. Yeah. Can I just interrupt for 1 second?
Sure.
So when you say the agent is playing the game, in some sense we also talk about machine learning system playing the game. So what does playing the game mean?
The thing that makes moves on the board is what I'd call the agent. And that's what I'd consider playing the game. But maybe I didn't understand.
I just want to make sure we're clear. So
we use machine learning to train an agent that will then play the game.
Okay.
Does that help?
It helps.
Okay.
Yeah.
The environment is the world that the agent plays in. It's the world that it gets to explore. It's going to make actions in this world, and those actions will typically affect the world in some way. Third, we have this notion of an observation, and the observation is what the agent gets to see of the world. Now, in some situations, the agent can see everything. In this situation, for example, the agent can see the entire tic-tac-toe board. There may be the others where parts of the board or parts of the game space are hidden. And in this situation, the agent doesn't get to directly see the other player. It doesn't have a notion of what drives the other player or other things interacting with this board. It just gets to observe the board. And it's sometimes helpful to just keep in mind that, like, okay, we have an environment and there's what the agent gets to see of it as separate things.
So the other agent might plausibly be, it might be a human being who's responding.
Yeah.
It might be another agent that is playing randomly.
Yep.
It might be another agent that's been trained on a different machine learning system, such as one that was trained by a supervised learning system.
Exactly. But the agent, while it's training, doesn't get any insight into that. It doesn't get to know anything about
Just
that.
sees boards.
It just sees boards.
Okay.
And then another important element is the notion of a reward. So in reinforcement learning, when an agent makes a move, it may receive from the environment a reward signal. And that reward is either going to be positive or negative. And it's much like positive or negative reinforcement to, maybe a dog that you're training or something. And this reward is a sort of signal of goodness or badness. Now, the reason I said it may receive a reward is that it generally rewards are sparse in reinforcement learning in that they just don't always come. So you may make a move and get no information. So the agent sort of has to learn to maximize reward over the long term. So in the case of tic-tac-toe, for example, we may only give it a reward at the end of a game. You won or you lost. And won should be a positive reward, and lose should be a negative reward. But for each individual move, we're going to pretty much give it no feedback. It's just going to have to keep exploring and figure it out. It's going to have to figure out how in the long term to get good rewards.
Is the frequency of reward something that the developer controls?
Yes. To some degree, the developer, and we'll talk about this later, this can be considered reward shaping. This is something in between sort of what's inherent in the environment, what can you draw rewards from, and what signals can the developer pass on to the agent given the state of the environment.
I don't want to anticipate what you may be about to talk about, but to the system, rewarding your dog, you give the dog a little food treat because it likes food treats. In this case, the system knows to prefer behaviors, so to speak, that were rewarded?
The system knows, and sort of the algorithm is written to maximize the reward. So positive rewards really have to be a positive number, and it's just trying to increase that number. It's trying to get the largest number. And that's sort of the dog treat that it likes. So that's sort of how the algorithm is written.
Okay, after all, isn't that what we're all after?
Big numbers. Up and to the right.
Oh, not. Go ahead.
One last thing that I'll talk about that was sort of interesting in the context of reinforcement learning is the notion of exploration versus exploitation.
Again, very nice.
And this is interesting because, and I'll describe what it is. So exploration is this notion that the agent has to explore the possibilities of actions in the world. When it starts, it doesn't know what's a good action or not. It just has to try out different things.
So it hasn't yet discovered that corners are good plays, if in fact that's the case, as we humans believe.
And exploitation is taking advantage of the knowledge you've learned of what is good. So when you discover that, let's say, corners are good, consistently taking corners. Now, this is a trade-off because when you're learning something, if you just stick to what you already know is good, you may not find something that's better. So you need to balance off exploring new stuff, which may sometimes just not work out, and exploiting the knowledge that you have already learned along the way. So in reinforcement learning, the sort of way this is done is at the earlier stages of training, you want to let the agent explore a lot more. So it won't always make the best move, but then over time, you make it exploit the knowledge that it has learned more and more and refine that rather than just randomly exploring stuff. So that was a really interesting concept for me.
Yep. Yeah, that is.
So those, I would say, are the core ingredients of reinforcement learning in general. Make sense?
Yes, it does.
Okay.
I do have one question.
Yep.
How do you, the developer, if you do, how do you tell the system what it's trying to do, what constitutes success? In the case of tic-tac-toe, it's winning games. We know winning games in a human three by three grid means a straight row with your counters in them. How do you tell the system what you want it to do?
Yeah. So when it makes a move on the board, the environment will just send back a reward number.
How does it know that it's aiming for what we would consider to be three in a row?
So I'd say the agent doesn't know, but the environment knows what winning is.
How?
It's the rules of tic-tac-toe. You check if the game is done. You check if anybody won.
It's placing random markers, counters in the beginning. How does it know that a game has been won?
So that's the feedback from the environment. So the environment is what contains the game logic.
How does the game logic get into the system?
So we program the game logic into the environment.
Okay, good.
Yeah.
Okay.
So it's very comparable to the game logic you programmed into your game generator. Yes. So the way you generated your data had the rules of tic-tac-toe. Here, the environment is the rules of tic-tac-toe.
When I was generating random games, it just put in random counters after each one. It had a very simple little routine to check if there were three in a row. You have supplied that as the developer to the system ahead of time.
To the environment, exactly.
Yeah, great. Okay, good.
So it can now play interactively with the environment, but the environment knows the rules of tic-tac-toe and is enforcing them.
So reinforcement learning in the Atari example, one of the famous examples, in the game of Breakout where you're bouncing a ball, so to speak, against a row of bricks and the bricks disappear when you hit them and you're trying to get rid of all the bricks. Somebody had to tell it that no bricks, that's success. That's the state we're looking for.
So I believe if I remember correctly, you get a point or a certain number of points every time you hit a brick. And it was basically like maximize that number. So there was no encoding of no bricks is the final state. It's just like make that number higher.
Which works out to the same result.
Yes.
Okay, thank you. I've long wondered about that intervention by the developer.
Yeah. So in that case, the video game of Breakout is the environment. So when a ball hits a brick, it disappears. Those are the rules of Breakout. Yep. So those are the ingredients of reinforcement learning at large. We still need to pick an algorithm to actually do the training. So reinforcement learning is an old problem. We need to pick an algorithm that will solve this problem for this agent. And the one I picked is the one from that Atari example, which is called deep Q learning.
Q as in the letter Q.
Q as in the letter Q. As far as I know, Q does not stand for anything, but it is the name of something that we'll talk about.
Okay. It sounds like Q should be silent then. But,
That's an interesting idea. Yeah. In terms of like, as far as I know, Q is not short for anything. It's just like Q. And so I'll describe what Q is. So in this scheme, Q is the notion of the goodness of a move. So in this algorithm, whoever wrote it, they were like, the goodness of a move we shall call Q in a mathematical equation. And the way it's formulated is it's designed to capture the immediate reward of making a move, as well as the maximum expected future reward of making that move. And I'm going to try and break that out. So you take some combination of like you get some reward now, and what is the best reward you can get in the future given the move you made now. Now, that involves sort of looking ahead in time. And it also takes into account that moves later in time may not be as valuable as moves now. Like often in situations, like a good move early is better than a good move late because you get yourself into a better position early and then you just sort of build off of that. So this Q value is sort of an equation that sort of captures this in a really nice way. It's a bunch of math, which we won't get into, but it was sort of fun to read about.
Okay, side note on Q. I just confirmed online that my memory is correct. A Q score is a measurement of how appealing a celebrity is, how much people just like that person. So Paul Rudd's Q score is way off the charts. Kevin Spacey's a very excellent actor. His Q score has taken, I imagine, something of a hit over the past couple of years.
Interesting. I wonder if it's related in domain at all. Did not know that.
No reason to think that they are related.
Yeah. So in deep Q learning, we have these Q values, and that's what the system is supposed to learn to estimate. It's supposed to learn to estimate how good a move is given the board state. And in fact, we want to learn to estimate, given a board state, of all the possible moves, we want to know what their Q values are. Because if we know that, we can pick the one with the highest Q value because that's the best move.
Okay.
Make sense so far?
Yep.
The other thing the DQN paper introduced was this notion of replay memory. And replay memory is an interesting construct, and it's basically a sort of memory of games past and of board states past. So as the agent is interacting with the world and making moves, it sort of stores those outcomes, whether there was a reward, whether there was no reward, in this replay memory. And it's going to draw from that replay memory later to sort of evaluate its later state against old situations, so on and so forth. So it's kind of interesting. It has this notion of a memory of old stuff that it can draw on, and it uses that to train.
Is it remembering old boards, or is it a weight that's added to a
No, this is remembering old boards.
So it's very different than the supervised learning that I trained the model on. We talked about this. It doesn't matter what game the board is. It's just a state of the board, and you're looking at it to see what the next best move is. It loses there is no memory at all.
Yeah.
So,
and in this case, the replay memory it's not in the network. It's just this external state that stores the board, the move that was made, what reward, if any, was given, and it just puts that in a list. An interesting thing about the game versus board thing, even in this algorithm, boards are taken from that replay memory randomly. It actually doesn't take them in sort of games at a time. It turns out that it's better to sort of shuffle these things and take them randomly, so you can periodically go back to really old games that you played and see how well you did on that board. Super interesting concept. And also a neural network. So DQN, we're doing neural networks.
DQN?
Deep Q network.
Oh, okay.
So deep Q learning, the network is a DQN or deep Q network. So we're going to use a neural network as the model underlying all of this.
So this training will generate a neural network that...
Yeah, so all of that I've described so far is sort of the algorithm that drives training. Like we discussed, the model is sort of that structure or architecture of the thing that learns. And here we're going to use a neural network, just like we did for your agent. In fact, I'm going to use pretty much the same structure that I sort of gave you when I was setting you up. So the type of model is the same. We're just using a different training scheme to help it learn.
Okay, good.
Make sense?
Yeah.
Yeah, we're getting the pieces together. We're getting the pieces together. And obviously while it's playing, there'll be an opponent. In this context, the opponent is just part of the environment. The agent doesn't really know. It just plays a move and somehow the board changes and there's some other symbols on there. But for me during training, I also used a random agent as the opponent. So when the network makes a move, the opponent just makes a random move.
All right, so let me ask you a question.
Yeah.
I would have guessed, which is a short way of saying I'm very likely wrong, I would have guessed that it will train better if it's playing against an agent that knows how to play tic-tac-toe.
I would think so. And yes, I would agree with that. But it's sort of a bootstrapping problem. Where do we get an agent that knows how to play tic-tac-toe?
Go to any computer science 101 class and ask for the kids' homework.
We could, but that wouldn't be fun. This way, we're just make random moves and let's see how far we can get. And then now that we have these two agents, we could look in future at training them against themselves and seeing how that does. That could be an interesting thing. But to start, it was kind of interesting, how far can we get with no strategy programmed in? The rules are there, but we've never programmed in a strategy of how to make good moves. And I think that's just an interesting challenge because in bigger problems, you often don't have that strategy. Yes, tic-tac-toe, it's easy to find, but we want an algorithm that can adapt to problems where we don't already have a solution.
I'll be very interested to see the results. The machines playing each other was, I think, sort of the second generation of AlphaGo, the breakthrough machine learning system that beat some of the best Go players.
Yeah, yeah.
And then so the next step was to have it play itself. And as I recall, it was already the best player on the planet, arguably, but it got amazingly better incredibly quickly because these games are,
Yeah, having strong opponents while you're training really, really does help.
Yeah, if you don't mind losing a whole bunch.
Which is,
that's why I prefer. I won't play chess with anybody over 5.
So those are the ingredients that sort of got put together for this. Before talking about the results I have so far, I want to chat a little bit about what are the other knobs to sort of tune or change. We mentioned sort of hyperparameters once or twice, and we'll probably get back into them more. But here, one thing I had to decide is how many games does it play? And I've tried a variety of things. I think for the first experiment that I'm going to describe, it was maybe something on the order of 10,000 games. It's a lot of games.
That's a lot of games of tic-tac-toe.
But they go really quickly.
Yeah. I was actually going to ask you, how do you decide how many games it plays? But you already answered.
I just picked.
You picked and tried. And
picked and tried. Yeah. And I've tried lots of other numbers of games too. Sometimes I just increase it and see does it do better. So yeah, 10,000 seems fine. Also depending on my patience and sort of how fast it goes.
Actually, I think that's a slightly interesting question. So for 10,000 games, roughly how long does it take? Are we talking minutes, seconds, hours, days?
We are talking minutes. And actually, the first time I put it up, like it was in the 10,000 was probably in the 15 to 20. But that was long enough that I wanted to make that faster. Because the faster you can do different things, the more fun you have and the more different things you can try and see what works out best.
Yep.
So that was one. The other was similar to a question you asked earlier of like about the rewards. Who determines the rewards? So I have to determine the rewards. And I said there's a positive number and a negative number. So I had to like pick all of the reward signals that the model would get. And I basically came up with giving it a large positive reward, aka the number 10, when it won a game, and a large negative reward when it lost a game, aka minus 10, and a very large negative reward when it got disqualified. So if the agent, because the agent doesn't know the rules of the game, if it, for example, makes a move on a cell or a space that's already occupied, that's what I consider a disqualification. And I'd give it minus 20 points.
Oh, wow, that hurts. And how about ties?
Ties, 0. There's no information given to it. There's no reward.
Why don't you want to discourage it from ties? Give it a slight minus.
We could. I was like, I don't know if I need to.
Okay.
I wanted to learn to win, and I wanted to learn not to lose or get disqualified. Hopefully it figures out the rest.
Okay. And if it didn't, you could try that.
We could try it, exactly. And even things like, do you give it any reward for each move? Like here, I just didn't. It's like you just play. If you play and the game hasn't ended, no info. So
Because you don't know it's a winning move until somebody's won the game.
Exactly.
Okay.
Yeah. So those are the rewards I picked, and I've also experimented with them a little bit.
So the equivalent thing in the supervised learning that I did was the data that I gave it to learn from was only games in which there was a winner.
Yes. Yeah, exactly.
So
yeah, that steers it in the direction of things that might lead to a win.
I didn't give it any stinking loser or ties.
Yeah, that's a great analogy of that. So yeah, that kind of thing. And then you train it, and then you let it train, and then you see what comes out, and you pit it against a random agent to see how it does in actual play. I also sort of captured a bunch of metrics, not terribly important, because the main thing is like, how well does it do in play?
And do you have results?
I do have results.
Is it worse than mine?
It is not worse than yours. So against a random agent, it gets about a 90% win rate.
Ooh. Okay.
So it does pretty well. I don't think that's terribly higher than yours. But interestingly enough, especially in those early experiments, it still gets disqualified once or twice.
Huh.
Like it'll play an illegal move. Like in a run of 500 games, 1 or 2 will sometimes end in disqualification by the agent.
Did you try to get rid of even that very small percentage of?
I did. I trained it longer, and that seemed to go away. But
Longer than 10,000?
Yeah, just more games.
What's the maximum number of games you trained it on?
At this point, I think I've tried like 30,000.
Okay.
And I just went 10,000, 15, 20, and then 30. And then here we are.
So at 30, you're not getting any disqualifications.
I haven't checked all along the way. I think somewhere along there, as it got higher, I didn't see any more disqualifications. I need to sort of run larger experiments. But yeah, at 30, I didn't see any disqualifications. I think even at 20,000, I didn't see any disqualifications.
And how is the win rate up in the stratosphere of?
No, it's pretty similar. It's still in the 90-ish range, as I remember. I didn't like record it furiously for all of that against a random agent, but it's 90-ish or so.
I mean, I hate to say it makes intuitive sense because that's a very bad way to be thinking about machine learning. But the world's greatest tic-tac-toe player does not win every game.
Yeah.
Right? I say that with a great deal of confidence. I really don't know if that's true.
You can successfully beat a random agent because generally that random agent has no strategy to win and will often just like throw games effectively. So yeah, do I expect it to win every single game? Not particularly. It doesn't always take the single best move because I want it to sort of allow it some variety even when it's picking its move. So it generally tries to pick the best move, but it can occasionally pick the second or third best move, and maybe those moves aren't so great. But I did that to allow it to be able to play a variety of different things, even given the same board position. So that's where I'm at.
Okay.
Got an agent.
Okay.
We both have agents.
You have a trained model. You have an agent that can use that trained model to play successfully against a random agent.
Yes.
There's really only one question left.
What is that, David?
I was hoping you'd tell me. It's.
I think we both know
it's
where
a-
this is going.
Yes, it's. The question is, at what moment will my agent crush yours?
Join us next time to find out. You've been listening to Tic-Tac-Toe the Hard Way with your hosts Yannick Asogba and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
And the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.